Hey guys, this is Andrew with HKN, and today I'm going to be talking about DSB-SC, which is a specific analog modulation scheme for communication systems. I want to remind you that this is all in a video series which we're doing to explain some of the parts of different digital systems, specifically this communication system, which I've drawn up here. So just to go over what we're doing for this system one more time is that we have some message bits 0 that we want to send to somebody else. We want to encode them. We talked about that last week and how to make a orthogonal basis set for signals so that we get an analog signal out that we can send. Once we have this analog message, which I've called M of t, we need to modulate it and have a signal here. The reason that we have to do modulation, which usually just means shifting it to a certain frequency band, is because whenever we have a communication system, there's only a certain a certain range of frequencies that you can send things over. So you need to put your message in that range, and more likely than not, your message has frequency components which are not in that range. So they have to be put in that range, and that's what we use modulation for. Once we modulate, we get a signal S of t, which we would then want to send through a channel, which is a lot of RF stuff, which I won't be talking about. We'll just kind of be simulating what happens to the signal going through the channel. On the receiver's end, you get a received signal, which I'm calling R of t. That's an R, if that isn't obvious. And then you need to demodulate it, just like we modulated over here. We need to demodulate it so that we get our base signal back, M of t. Hopefully, we can get M of t back after demodulation. And then once we have M of t, we can decode because we know how we encode it over here. And we should be able to get our bit stream back. And that's what the program that we wrote is going to do. So we want to explain to you the different parts of the system. Last week we did encoding and decoding. And so now this week we're going to talk about everything in this box here, which is modulation and demodulation. So we're going to talk about how given M of t, we can get S of t, or given R of t, how we can get M of t. We're going to talk about what happens inside these two boxes. And so there's a lot of different ways that you can modulate. And so the way that we've chosen to do it is that we're going to use DSB-SC, which stands for double sideband suppressed carrier. And so from the name of it, you might be able to figure out what it means. It basically just means you're getting both sides of your frequency band, so the positive and negative side are being sent. And suppressed carrier means that we're not sending any information about the carrier through our transmission system. So DSB-SC is really fairly easy to talk about. So we have a message, M of t, as just some general signal. It could be any voltage varying signal. But for simplicity's sake, I'm going to say that if we take the Fourier transform of M, that we're going to end up with a couple of triangles. Or actually just a single triangle. So this guy will have height AM. And it goes out to frequency B and negative B. So it is a triangle function. So that's the message we're going to be considering when we're talking about here. This will work for any real signal M of f. So M of f has to be symmetric about the origin. Not about the origin, sorry, about the vertical axis. So this is nice. We have a frequency which is between negative B and B, but we're told that, and so this, so the 2B length here is going to be within the allotted amount of bandwidth that we have. So the government or whomever is giving out the allotments for where your message has to be and how big it can be tells you that your frequency, that the amount of frequency of the band that you can take up is definitely at least less than your message 2B. They won't tell you that, they'll tell you how much, but you can figure out that it'll be less than 2B. We're making that assumption. So the bandwidth that we can transmit over, so I'm going to say BW that we can transmit over, is less than 2B. Sorry, greater than 2B. So So we want that to be greater than 2b so that we can send our full signal both sides of it. So what we need, but they tell us that we need to send at some frequency FC. For instance, FC could be something like 200 kilohertz, for instance. We're just going to use FC, but a normal number is something in the kilohertz range. So then what we have to do is we have to move this message out to the 200 kilohertz range without distorting it. And so what we do in order to do this is we kind of just multiply by a cosine. I know it sounds very simple, but it actually works very, very well. So if we think about what multiplying by a cosine does, so we have our input message m of t here, and we're going to multiply by a cosine at our carrier frequency, 2 pi fct. And out of here, we get our signal s of t. And so that seems very simple, but what happens here is that if we look at the when we multiply in the time domain, we convolve in the frequency domain. So if we look at the frequency transform here of cosine, the frequency transform of cosine, and I'll just call this h of f because it's kind of like a filter, not really, but h of f here is 2 delta spikes centered at fc and minus fc. And so if we convolve this function here, we know that if we convolve any function with a delta function, it just takes this, this message and is going to just shift it to be centered at the delta function. So we take this entire thing, we kind of just pick it up and move it onto this, the delta function. So finally, our signal is going to look something like this. In the frequency domain, S of f is going to look something like this, where we have fc here. This is drawn wildly not to scale, but I'm hoping that you'll get the idea. Minus fc, and we get the triangle again. And so these are centered at plus minus fc. And these values out here are fc plus b and fc minus b. And I'm sure you can interpolate what the values over here are. But the point is that we took both sides of this band, shifted it out to the point that we wanted, and also, by necessity, we get the other side, so that's still a real signal. So we've actually doubled our bandwidth here, which is not something that's very good, which is why DSB-SC is not used directly in most systems. But it accomplished what we were looking for, which was to take our message and put it to the band at which we can transmit over. So we would take our signal S of f or S of t, however you want to call it, and transmit it through the channel. And so right now we're going to assume that our channel is going to do not very much to our signal. We're going to assume that it's kind of a one-to-one relationship, that whatever we put into the channel, we're going to get out. And that is not true. We should get some attenuation and some noise, which we will ignore for the purposes of this, because we can't really know what that's going to be. The noise is going to be random, and the attenuation is actually just kind of scaling, so we can always just scale it back. And actually, even more generally, when I said we're multiplying by that cosine, we can multiply that cosine by any kind of amplitude that we want or that our power budget allows us. So I'm going to leave this here because this is the thing that we want to recover on our receiving end. So on our receiving end, we have R of t, where R of f looks like our signal that we sent, probably with some noise, but we're going to ignore that for now. So we have this guy here, minus fc plus fc. So again, want to take this R of t and do something to it, maybe pass it through a couple of filters, and get back our original m of t. And so the easiest way to do this is to multiply by a cosine again. Again, it sounds really simple, but it works. So all we do is we take our R of t, multiply it by a cosine, and there's one actual caveat on this, and that is that we then need to take our signal and low-pass filter it. And I shall show you why in a second, and we should get back m of t with some scaling out in front. So that scaling can be, we'll call it b. It's some function of the frequency of this guy's frequency and this guy's amplitude. Not so much the frequency, just the amplitude, and a couple of 1/2s that arise from the Fourier transform of a cosine. So I'll just call that bm of t, and you can always scale it back up to where you want, or avoid that by putting some 2's wherever you multiply by a cosine, so that you just get delta functions and not half delta functions. So what we want to, so the reason that we have to do these guys is, so let's just first apply this. So we get, sorry, that was a little confusing, but we're just going to first just apply this and see what happens, and it'll make sense why we do it. So again, if we are taking a multiplication in the time domain, we take a convolution in the frequency domain, and that convolution is with 2 delta functions at fc. And so, if we look at what happens to our signal in the frequency domain, what happens to R of f when multiplied by this cosine, so this is the Fourier transform of cosine again, 2 pi fct. What we find is that we take this whole thing and center it at fc, take this whole thing, center it at minus fc, and that the addition of those two is going to be our our final signal, our decoded message. This is what m of t should look like. So I guess this would be m of f because we're going to be writing the frequency domain. So what we get is we take this guy, shift him here. So this is centered at fc, so 0 is now at fc, which means if we shift this guy back minus fc, we're back at 0. So we get a copy of our message at 0. We also get a copy of our message all the way out at 2fc. So that kind of makes sense. And if we do the other delta function, we center 0 at minus fc, which means if we take this whole thing and place it here, that we're going to get a plus fc is going to center it at 0 again. So this actually just gets added on top again. So there's 2 of these. And we also get one at minus 2fc, which isn't surprising because we want this to be symmetric. And so if you notice, I haven't written the amplitudes in here in a while because you get a lot of 1/2s from multiplying by cosines. But what you'll find is that you need to multiply by 2 somewhere. This will probably have about half the amplitude, depending if you use what you use as the modulating amplitude for the cosine that you're modulating by. Or when we did the modulation step, we multiply by cosine 2 pi fc. You can also multiply it by 3 cosine 2 pi fc or 4 cosine 2 pi fc. There's reasons for doing that, which I won't go over now. But the point is that we have a kind of what we want here. Just we have a lot of extra stuff out on this band that we're getting back, which is going to mess up what our signal is. But if we know, but that is where this low-pass filter comes in. So if I then take a low-pass filter here and only take the stuff inside of that box, I get back my original signal m of f, which is what we were looking for. And so that's how DSB-SC works. It's pretty much you multiply by a cosine to bring it out to the frequencies that we were looking for, send it, and then when we get it back, you multiply by the same cosine, has to be agreed on by both the transmitter and receiver, and you get back your original signal after some low-pass filtering. And so if that kind of approximate analysis with Fourier transforms and some convolutions didn't make sense, we can take a look very quickly at some math just to make sure that this works. So I'm going to erase our message here because I need some room to do some math. So if we look at this, what we get is we're going to take our message, m of t, and multiply it by cosine squared 2 pi fct. And so the reason it's cosine squared is because you multiply cosine once to modulate and then cosine once to demodulate. And so we're going to also low-pass filter. This is my notation for low-pass filtering, this figure. So the first thing we know is we know that we have the double angle formula, that cosine squared of 2 pi fct is equal to 1/2 plus 1/2 cosine of 4 pi fct, or if you prefer, 2 pi 2fct. So that makes sense because we got frequency components at DC, which was our original signal, and we got frequency components at 2fc. So it works out. So let's plug in this, and we end up with, we want the, well, let's use the same color. So we want the low-pass filtered version of 1/2 m of t plus 1/2 m of t cosine of 2 pi 2fc t. And if we take the low-pass filtered, so let's apply the low-pass filter. We're assuming that the low-pass filter's frequency was chosen smartly such that it gets rid of higher frequency things. And when we talk about higher frequency, we say stuff at out beyond 2fc. Kind of be silly to use the stuff at 2fc, especially if we're modulating at something so large as 200 kilohertz. Why would you think that you'd have a message so far out as 400 kilohertz? It would be a little silly. So when we take the low-pass filtered version of it, we just get the DC component out of it. So we end up with 1/2 m of t, which is what we were looking for. We got some multiplication factor of our message out on the receiving end. And so that's what we were looking for. That's how DSB-SC works in modulation and demodulation after going through some channel. Last week we went over how to encode into the signals that we will then modulate. And then once we have the received signal, how to decode it. We did that using signal space last week. And so after this, we have probably one more topic, and then we're going to talk about how to do all of this in MATLAB. So until then, I'll see you guys, and have a nice day.